Good morning. I'm just going to give a few more minutes to let everyone join in, and then we'll get started.
Okay,
All right.
ready to start, right?
Yep. Good morning. Thank you for joining us today for our webinar on solvent recovery. I am Carrie Bennett, the marketing coordinator here at Koch Modular, and I'll be moderating today's session. We appreciate you taking the time out of your day and hope you find this webinar both insightful and beneficial. Joining us to present on solvent recovery is Tom Schafer, co-founder and vice president of Koch Modular. Tom holds a Master of Science in Chemical Engineering from Manhattan College and has obtained 45 years of industry experience. His expertise lies in the area of equipment design, including distillation, heat transfer, fluid flow, and process controls. In this webinar, we'll be... Oh, my slides aren't going. There they go. In this webinar, we'll be diving into the major benefits of solvent recovery, the correct sequencing for techno-economic viability evaluations, along with real-world examples and lessons learned. I'm sure many of you will have questions during the presentation. Please use the chat window on the right-hand side of your screen to submit your questions, and we'll answer as many as we can at the end of the presentation. Following the webinar, we'll provide an email that summarizes all questions and answers along with a link to the recording of the presentation. Thank you again, and now I will hand it over to Tom.
Okay, thank you, Carrie. Again, hi to everyone. Thanks for attending. My name is Tom Schafer. I am a chemical engineer, process engineer by background. And today I'm going to talk about the subject of solvent recovery. And the highlights of today's presentation will focus on the benefits to you as a client in recovering solvents. And the correct sequence of steps that a chemical engineer will take to evaluate the viability of installing a solvent recovery system. And then at the end, I'm going to talk about 3 example projects. One is the simplest one, which is a 1-column system for the recovery of denatured alcohol. Second one was a more complex system for the recovery and drying of acetonitrile. And then the third example will be a methanol recovery system where energy consumption was a major concern and priority of the client, and we came up with a relatively unique design for that. So I'd like to start out, if you're not familiar with Koch Modular, with a brief overview of the company. Koch Modular is actually a joint venture company between Modular Process Systems, Inc. and Koch. And Koch, as most of you know, is one of the world's leading suppliers of mass transfer equipment, packings and trays, for example, that go on the inside of distillation columns. Koch, in turn, is owned by Koch Industries, and Koch Industries is one of the largest privately held companies in the United States. As you can see on the right-hand side of the slide, we've been in business for 40 years, including all of the predecessor companies, and we currently have about 100 employees. We are really good at solving difficult separation problems, and many of those types of problems come up in solvent recovery applications. So we serve not only the oil and gas and petrochemical sector, but we serve the entire chemical process industry, including, as you can see here, pharma, biotech, specialty chem, performance materials, biofuels, mining and metals, flavors and fragrances, agricultural chemicals. So we have a pretty broad brush of experience, and let's go on to our next slide here. So our core strength is process design. I mean, that's where it all begins for us. We add the most value to customers' projects when we are faced with difficult separations, non-ideal mixtures, breaking azeotropes, low relative volatility systems. Clients bring us in to tackle those tough problems. And this eventually involves us getting involved in pilot testing in some cases, and then the delivery of modular systems. We have a pilot plant that's located in Houston, Texas. And typically what we'll do in this pilot plant is after we develop conceptual process design, if we don't have adequate vapor-liquid equilibrium data, liquid-liquid equilibrium data, we can measure that in the pilot plant, and we can set up a process on a small scale, and using real feed from the client, like 55-gallon drum quantities of customer feeds, we can set up the process and run it to de-risk it. And of course, the end product that we provide is usually a complete process system, which includes all of the equipment, piping, instruments, and controls. So we have, again, over 40 years of experience building modules. They can be pilot scale, demo scale, or full commercial scale systems. Okay. So obviously, since we're talking about solvent recovery, we wanted to kind of cover what solvents really are. A solvent is a substance, and it's usually a liquid that is able to dissolve other substances, such as solutes, and form a solution. So solvent recovery or solvent reclamation makes it possible to recover and recycle the solvents, which results in a much more economic process for the client. So an example of some of the solvents that we have recovered at Koch Modular can be found on this page, which includes all of the alcohols listed, a fair number of ketones, aromatics, aliphatics, acetates, chlorinated solvents, and then under the final group below, you see a mixture of other, mostly polar solvents that we have recovered. So why should you recover solvents? The benefits of recovering solvents are many. The main ones are reduced operating cost and reduced operating expense. So the cost of solvents are expensive, and if you have to replace them after one use, that's clearly a major expense to your operation. So if you can recover them, you save that expense. You also reduce the cost of having to dispose of the solvents if you choose to dispose of them. Some people will incinerate them, which is not an environmentally friendly thing to do. So others will actually take their solvents and ship them off site to a toll processor and recycle them that way. But taking them on site, gives you a lot of advantages. And of course, the inventory of solvents that you have to have as an operation can be reduced if you recycle the solvents on site. So that reduces your working capital. So economically, there are a lot of reasons to recover solvents. It's interesting, we're doing a project with a pharmaceutical company, and they mentioned to us the other day that because of the shortage of oil, solvents, for the most part, come from petrochemicals. But because of the shortage of oil and gas, they have short supply of heptane and THF, for example, that they use in the manufacture of their active pharmaceutical ingredients. And they basically said if they couldn't recover the solvents on site, they would experience fairly severe upsets in their supply chain and outages in the ability to manufacture their active pharmaceutical products. Of course, there's a lot of environmental benefits to recovering solvents. I mentioned some of them already. It's a green approach. Recycling is really a popular approach today, and it restores valuable resources as opposed to incinerating or disposing of solvents. A lot of the projects that we get involved with, the clients also have aqueous wastes that have smaller amounts of solvents in them. And it's very common for us, in addition to supplying a solvent recovery system, to supply a steam stripping system to recover the solvents out of their wastewater. And then the solvents that are recovered from their wastewater are combined with recovered solvents and go through the solvent recovery system. And obviously, having a solvent recovery system makes it easier to comply with EPA regulations. Another reason why you ought to consider recovering solvents on site is that you can have better control over the quality of the recovered solvents. If you ship your solvents off-site to a toll processor, those toll processors use common equipment for many different separations, and you can risk having foreign substances get into your product. So, last but not least, if you are shipping solvents off-site, you retain the liability for those solvents while they're on the road. And if you don't have to ship them, that just reduces your liability. So now I'm going to go through the steps, a sequence of steps that engineers consider when they want to design a solvent recovery system. So the first step is critical, and it needs to be done in order to establish a design basis. Basically, it's the material balance that you're looking to achieve around the solvent recovery system. So you need to, if you have multiple sources of the solvent mixtures that get mixed together, you need to determine the composition of those solvent mixtures, including all of the impurities and solutes that can be present. It's very important to understand all of the impurities that can be present, and of course the quantities of the solvents that have to be processed. Do you produce streams? A lot of times our clients produce, especially in the pharma industry, produce solvent streams on a batch basis, and they have a range of expected flow rates and composition. So we try to get them to define that. And of course, as I mentioned, define the composition and the quantity of their aqueous waste, if that is to be included in the picture. Go on to the next slide here. Okay, so again, that is the first step, determining what your solvent mixture is, what all of the impurities are, and its flow rate. The next step is to determine the purities of the recovered solvents that you want to get back from this recovery and recycling process. And typically, it's normal to expect that the goal would be to purify the recovered solvents to the same set of specs as the virgin solvent purity that you buy if you were to buy a virgin solvent mixture. Okay. You also need to know, in addition to the feed flow rate composition and recovered product composition, you also need to know what utilities are available to heat and cool the process. Most of the processes involve some form of distillation where energy has to be put in, and then that energy has to be taken back out into a heat sink. So typically, the utilities that clients will provide us are steam to heat a reboiler, for example, or hot oil. So we'll need to know the steam supply pressure. We'll need to know the hot oil supply and return temperature and the type of hot oil that you have. For cooling, typically the cooling media is a cooling tower water. So we'll need to know in the summertime what the maximum cooling tower supply temperature is and what the expected return temperature is. And sometimes clients will also need to supply chilled water or some type of refrigerated coolant. So we'll need to know what those supply and return conditions are as well. So after we've got that information, we know the species that are present in the customer's feed and what purities we're trying to achieve. The next step is for us to evaluate the basic data that we need to develop a process, which would be the physical properties of all the compounds in the streams, including their boiling points, the normal boiling points, their vapor pressures, their molecular weights, the solubility in water, and their densities, sometimes their melting points. And then we have vapor-liquid equilibria, liquid-liquid equilibria data from a number of sources that we will look at to evaluate the process that we might use. We look to see if we have azeotropes, for example, constant boiling mixtures. And these data describe, the VLE and LLE data describe the relationships between the pairs of compounds that we're trying to separate and tell us how difficult the separation is. If we don't have adequate vapor-liquid equilibrium and liquid-liquid equilibrium data, again, as I mentioned, in our pilot plant in Houston, we have the equipment and the experience necessary to measure that data, which would then allow us to do process simulation work. So using all of that information, the first step is to conceptualize a process. In general, we usually start with distillation because that's the simplest technique. And then if we need other unit operations in conjunction with distillation, such as liquid-liquid extraction or melt crystallization, we'll use those concepts in the preliminary part of our design. So on paper, we kind of conceptualize a process, and then we use a process simulator. In our case, it's Aspen Plus, to computer model the process that we've come up with and determine the number of steps required, how many distillation steps, how many other steps are required in order to meet the customer's goals for purity. And then, of course, we'll learn from the process simulation what the yield of the recovered solvents will be and the preliminary energy requirements, utility requirements of the process. We'll also evaluate the materials of construction for the equipment and the process piping in our process. And then we typically prepare a preliminary flow sheet or a P&ID. All of this to be used in cost estimating. After we've developed the process simulation, we usually have enough information where we can calculate preliminary sizes of the equipment, of the solvent recovery equipment. And then from there, again, using the equipment sizes and the P&ID, we can generate a rough budgetary capital cost for the solvent recovery system, and also make a list of the operating costs. There may be more than one candidate process for us to look at. Usually we narrow it down to one or two during that conceptual design phase, but there may be more than one. And at the end of this conceptual design, we usually have a discussion with our client and make a recommendation on the candidate process that we would like to, pursue. And we also know at this point in time if we need to do some pilot testing or not. I would say in most cases, we don't need to do the pilot testing for distillation because we usually have in our database enough vapor liquid equilibrium data to allow us to confidently model the process. So moving forward, if we do need to do the pilot testing, or the client, for example, wants to actually take some of their feed material and test out the conceptual process, we can do that. So typically we work with 55-gallon drum quantities of waste solvent, and the client will ship those to our pilot plant, which is located in Houston. We will analyze, the client and us will both analyze the drums. And if the drums don't contain what we consider to be the worst case set of conditions, then what we can do is we can spike the drums with impurities to get to what we consider to be the worst case conditions, and then use that for the testing. Typically, a client will provide us analytical procedures to be used during the testing, but we can, jointly, we can develop additional analytical procedures if necessary to measure all of the impurities, in the pilot test. So we'll set up a process in the pilot plant that basically mimics, what we developed in the process simulator. And then we'll run that process and observe how it works, determine, whether we're getting the purities that we need. Sometimes we'll see that there are other impurities in the client's feed that they did not report to us initially, and then we'll have to figure out how to deal with those other impurities. That happens fairly often. We'll also find out whether there's some gross fouling or foaming that takes place in a distillation column. The columns that we're using for the most part are glass, and so we can see into them. And then after we've done the test work, we'll summarize our findings in a report, and then send the recovered solvents, the quantities of solvent materials that we've recovered during the testing, back to the client for them to do further testing on. Sometimes they'll do use testing with those. So the next step is, if we do the pilot testing, is to compare, what we found versus what we modeled, and then make any adjustments to the process design, make any adjustments in the cost estimate and the quantity of utilities that are used in the process. And then from there, if the economics look strong, the next step for us is to prepare a formal process design package for that process, which would include a process flow diagram with heat and material balances, P&IDs. We would make lead sheet drawings of any fabricated equipment, columns, decanters, reflux drums. We would use Aspen shell and tube to design all of the shell and tube heat exchangers. We would develop preliminary pump sizes and a preliminary equipment general arrangement drawing to determine how many steel structures and what size steel structures that we would use to house the solvent recovery equipment. I'm a slide behind you, excuse me on that. So I was just covering point E there. So, and then we would typically participate in a PHA, a process hazards analysis with the client, make any adjustments to the process design package, and then from there, we have enough information to develop a fixed firm price to do the detailed design and construction of the solvent recovery system with full performance guarantees at this point. And of course, we would also give the client a detailed project schedule to complete that work. Once we give that to the client, it's up to them then to make a final decision about whether to go forward with the project or not. So that is the process that we follow to evaluate a solvent recovery application. Okay, so now I'm going to go into some examples of solvent recovery systems that Koch Modular has designed and built. The first one is the simplest, as I had mentioned early on in my presentation. It's a one-column system. The feed to this system was from a pharmaceutical client. It was a stream containing approximately 30 to 35 weight% of a denatured ethanol. So that means a 95:5 ratio of ethanol to methanol in water. And the client's feed also contained some proteins. So there was a step upstream of the distillation that the client used to dissolve the proteins. And then that stream would be fed to the distillation column. And the client's goal in this application was to recover a denatured alcohol that was approximately just shy of 94 weight% alcohol. So the 94 weight% is the combined ethanol and methanol in that stream. So that was their goal for a recovered solvent, and the bottoms of the column was wastewater. And the client's goal there was to strip the alcohol out so that there was less than 100 parts per million of alcohol in that wastewater. And as you can see from the flow sheet, this is again a relatively simple process where we take the feed that comes out of a storage tank. We preheat it against the boiling water effluent that comes out of the bottom of the column. So we preheated the feed close to the boiling point, and we feed it into the middle of a column that has both rectifying stages and stripping stages. There's a lot more rectifying stages required in this separation than stripping stages. And the reason for that, so you can see the VLE that we were dealing with here. So again, we had methanol and ethanol, and this is the methanol water VLE. There are no azeotropes, and this is a relatively easy, straightforward separation. But the bulk of the alcohol is ethanol, and our goal is to get here, if you can see my arrow, is to get up here in the neighborhood of 90 weight% ethanol. And, you know, the equilibrium pinches, and there's actually, at atmospheric pressure, there's actually an azeotrope between ethanol and water. So most of the stages are up in this region of this diagram. And so in reality, most of the stages for this system were above the feed. So we designed and built a system. It took us about a month and a half to do the process design package, and then about another 10 months to do the detailed engineering and delivery of the system. I'm going to take a little sip of water here. And that system's been in operation for approximately 10 years now and working just great. Okay, we're going to move on to another solvent recovery application that's a bit more difficult of a separation. It involves, again, a pharmaceutical client in Puerto Rico. It involves the separation and drying of acetonitrile from a mixture that had about 17%, 17.5% acetonitrile in it. The balance was mostly water, but there were some low boiling impurities and some higher boiling impurities in this feed. And so we designed and built a 3-column system. It took 3 columns to generate a product that satisfied the customer's requirements. The first column was relatively straightforward. It was there to remove lower boiling impurities, impurities that were lower boiling than the acetonitrile. And then we used to dry the acetonitrile, to recover and dry the acetonitrile. There is an azeotrope between acetonitrile and water, and at atmospheric pressure, that azeotrope is roughly 86, 87% acetonitrile by weight. So in order to dry the acetonitrile, we were going to have to overcome the azeotrope. And we used a technique called pressure swing distillation for this application. And pressure swing application is a distillation technique where you have 2 columns, one that operates at a low pressure, one that operates at a high pressure. And if there is a significant shift in the azeotropic composition versus pressure and sufficient relative volatility between the compounds once you get on the other side of the azeotrope, then this can be an economical method of separating 2 compounds that form an azeotrope. It has to be a homogeneous mixture, though. Other examples, I know we're going to talk about acetonitrile and water, but other examples of mixtures that we have separated where we used pressure swing distillation include THF, water, that's a fairly common one, ethanol ethyl acetate, propanol toluene, and methanol methyl acetate. So for the acetonitrile water separation, this is a McCabe field diagram that demonstrates how it works. So the low pressure column is demonstrated here on this using the green VLE data, green colored VLE data here. So basically the feed comes in here, and we're easily able to strip the acetonitrile out of the water to get down to a very low concentration of acetonitrile in the low pressure column. And then above the feed, we have stages that basically, get us up to the azeotropic composition. And in this case, we actually operated the low pressure column under vacuum. And so the low pressure column produced a distillate product that was 89 weight percent acetonitrile, 11 weight percent water. And then we took that distillate and fed it to a pressure column. And in the pressure column, in this case, it was 70 psia, that was the operating pressure. The azeotropic composition shifted to about 77 weight percent acetonitrile and 23 weight percent water. So since this is a minimum boiling azeotrope, when you feed an 89% acetonitrile feed into this high pressure column, all of the water goes overhead, and then dry acetonitrile, comes out the bottom of that column. Here's a flow sheet for that process. So the low pressure column, as I mentioned, actually operates under vacuum, and we had a steam ejector for that purpose. And then the high pressure column, again, as I mentioned, operates under elevated pressure. So just kind of walk you through the process in a little bit more detail here. Again, here's the low pressure column and its vacuum system, and here's the high pressure column. So the feed containing the 17.5% acetonitrile is fed into the middle of the low pressure column. Wastewater comes out the bottom with only a few parts per million of acetonitrile in it for disposal. The overhead product, as I mentioned, is collected in a reflux drum. Some of that is refluxed back to the top of the low pressure column. And then I'll go on here. I mentioned this already, so let me skip through there. So then the 89 weight percent azeotrope produced in the low pressure column is fed to the high pressure column. And overhead comes a 77 weight percent azeotrope with all the water in it. And that gets recycled back. You follow this process, that gets recycled back around to the feed. That recycle stream gets recycled back to the low pressure column, so that the only place water leaves the system is in the bottom here. And then dry acetonitrile comes out the bottom of the high pressure column. And in this case, the goal was to have less than 1,000 ppm. We ended up achieving about 100 ppm of water in this recovered acetonitrile product. And again, here's the recycle stream that we talked about. So usually the greater the difference in pressure between these two columns, the greater the difference in the azeotropic composition, and the smaller the recycle that has to go back around to the low pressure column. So we had a pretty significant shift in the azeotropic composition. That's one of the reasons why we decided to run this column under a moderate vacuum, because it shifted the low pressure azeotrope even more. Okay, last but not least, the third example that we're going to talk about is a methanol recovery system. This is a process that we developed for a company that makes water treatment chemicals. They had a fairly large flow rate stream that contained methanol and small amounts of isopropanol and water and some salts. And so we ended up designing a process and supplying them a system which I call a hybrid system. And it included two columns, a stripping column, which was mounted here inside the module, and then a column to separate methanol from isopropyl alcohol mounted here on the outside. So this second column was too large to fit into a road transportable module. So we ended up supplying this as a freestanding column, and then having all of its supporting equipment located inside the modular frame. You can see a picture of it here. This is a 3D model of it here. So that system replaced an old distillation system that was built for a different purpose. It was repurposed. It was not the right metallurgy, and so the equipment that it replaced was corroding. There was enough sodium chloride present in the feed to cause stress corrosion cracking. So the new system that we supplied, we ended up in the stripper, we ended up making this all out of duplex stainless steel so that we wouldn't have that issue again. So this process is rather unique in that we basically halved the energy consumption of a one column process. So what we ended up doing was we built a stripping column, a trade stripping column that operated at about 50 psig, and we used the vapors of that column to reboil the second column. So the second column did have a trim reboiler for startup, but essentially, second column that separates methanol from isopropyl was the energy for it basically came from the condensing of the vapors from the first column. So we significantly reduced the client's operating costs. And again, since the flow rate to the system was rather large, it was easy to justify using this what we call double effect distillation scheme that you see here. Okay. Carrie, I think I'm going to turn this back over to you now.
Yeah, thank you.
And
Thank you,
hopefully
Tom.
you've got some questions that clients have brought forth.
We have some active participation in the chat. So
Okay.
let's start with question 1. When is distillation used versus evaporation for solvent recovery?
Okay, that's a good question. We do get inquiries for quote unquote solvent recovery. And then when we get talking to the client, we find out that it's basically desolventizing a mixture that just has a solvent and a solid in it. So when you just have a solvent and a solid, no other impurities, basically the solid has almost no vapor pressure, and you can use a very simple evaporation process to recover the solvent from that type of feed mixture. And depending upon the concentration and the nature of the solids, that can be something as simple as a flash evaporator system, or if you need to get relatively dry solids and the quantities are large enough, you might have a flash evaporator system coupled with, say, a thin film or a white film evaporator to try to get essentially all the solvent out, away from the solids and generate a relatively dry solid mixture. So that's how evaporation would be used. And then if in fact, as I mentioned, you have the solvent, you have solids, and then you have other impurities that boil that need to be separated from the solvent. Could be water, could be other solvents, could be impurities. If they boil and there are challenges in separating those other impurities, then that's where you would not be using straight evaporation. You'd be using some form of distillation or possibly some other unit operation to separate out and recover that solvent. Okay.
Awesome. The next one is, I saw you mention liquid-to-liquid extraction in your presentation. When would you use LLE in a solvent recovery process?
Okay. So we use LLE in a solvent recovery process, for example, if there's a lot of water present. So if the solvent is, if one of those aqueous waste streams that the client has in their process it has a solvent in it, let's say acetic acid or phenol, or or DMF or something like that, dimethylformamide. If there is a lot of water that has to be separated, and water is a low boiling component, and the solvent is a higher boiling component, then it usually doesn't make sense to put in all of the energy required to boil off all the water. So what we will typically do is extract the solvent away from that aqueous mixture into another solvent and then separate it that way. We also use liquid-liquid extraction to break azeotrophs. Methanol hexane, for example. We can water wash polar impurities out of nonpolar solvents, for example. That's commonly done. So liquid-liquid extraction can be used to make a separation that would not be economically feasible to make by distillation alone. So that's how we would use it.
Awesome. Here's another one. Do you only design continuous solvent recovery processes, or do you also design batch solvent recovery?
Good question. I would say most of the solvent recovery systems that we build are continuous, but it's not uncommon in, say, the pharmaceutical industry or the specialty chemical industry, where the starting mixture that we have, the flow rates of that mixture are not large. It might be, maybe a couple of thousand gallons or a couple of hundred gallons a day of that mixture. And there are a lot of different impurities that have to be removed. And in a continuous process, you might have to have multiple columns, distillation columns in series to remove each one of those impurities. So, again, in a situation where we have multiple impurities and relatively small to modest size volumes of waste solvent need to be processed, it's often more economical to build a batch solvent recovery system, meaning you charge the waste solvent into a still pot, and then with a single column that's mounted on the still pot, you take off cuts of various impurities, and then eventually you take off a purified product cut from that single distillation column. So it's a capital cost consideration, practicality situation. But yes, we've done both continuous and batch distillation.
Okay, here is the next one. Can you design a multi-purpose solvent recovery system that can handle multiple solvent mixtures that would be campaigned?
Okay, yes, we can, and we have done that. And I don't want to take things to the absolute extreme, but I would say, we earlier in my career, I worked on a multi-purpose solvent recovery system where the client had 20 different products. This was a pharmaceutical company. They had 20 different active pharmaceutical ingredients that they were making at a plant site, and each one of them generated different solvent mixtures. So it took a fair amount of engineering, process engineering, as a starting point to evaluate each one of those solvent recovery requirements. And then at the end of that, compile a system design that had all of the requisite equipment needed. In some cases, it required batch distillation, continuous distillation, and liquid-liquid extraction equipment all in one system. But again, as you can imagine, that's a complicated problem if you have a lot of different solvent feeds to evaluate, and then pick out one set of equipment that can do all of those things. But it can be done. It can be done.
Awesome.
Okay.
So here's another question. Can we increase capacity for distillation for existing systems? If so, how?
Yes. The first step, obviously, is the evaluation of the process. So if you have an existing solvent recovery distillation system, typically we would want to understand or simulate the process, and then evaluate the equipment to see what is the bottleneck. It could be the distillation column. It could be the capacity of the internals in a distillation column. It could be the heat exchangers, the reboiler and the condenser that work alongside of the distillation column. But we can do a debottlenecking study to try and determine if there is additional capacity that can be easily had from an existing system.
Awesome. And here's another one. What is the largest diameter and height distillation column that Koch can include inside a road transportable module versus needing to install a freestanding unit outside modules?
Okay, so road transportable modules in the US usually have, in a vertical modular system, where you have a column in that, the footprint of those modules when they are resting on a foundation usually is maxed out at about 12 feet by 14 feet. So you've got a 12 feet by 14 foot envelope, 80, 90 feet tall. Let's say, of course, we can stack modules on top of each other, so the height is not really an obstacle, it's the footprint. So considering that you've got that column that has to fit inside of that 12 foot by 14 foot envelope, along with a reboiler, a condenser, a reflux drum, piping, instruments, etc., we find that if the diameter of the column is more than about 6.5 feet in diameter, it becomes a challenge to have enough room to do a maintenance and to have enough access for operations for that system. So once we get above 6.5 feet in diameter, we typically will install the larger column outside of the frame as a freestanding column, and then have operating platforms, ladders and platforms on that column, and then you can access that column from the module. Hopefully I've answered that one.
Okay. What are some techniques that Koch uses that help with distillation applications that foam?
Okay, good question. So if you have distillation applications that foam, you have the choice of using a anti-foam, which is usually a chemical that you can inject. In a lot of cases, they're silicone-based silicone-based chemicals that you can inject into the feed. If you cannot afford to put a foreign substance like an anti-foam into the feed or into your equipment, then I would avoid the use of trays in the column. So you have inside the column, you have the choice of using different types of internals. You can use trays, or you can use packings. They work completely different. Basically, a tray is a device that is intentionally designed to create kind of a frothy vapor liquid mixture on each tray, and the area created in that froth is where the mass transfer occurs. So you're basically bubbling the vapor through openings in a tray deck. And if you have a system that foams, then typically the tray is going to promote the formation of the foam. So in a foaming system, if you can't use the anti-foam, then I would recommend using packings. If the system is also fouling, then I would avoid structured packings and I would use dumped packings, because dumped packings are easier to remove and to clean than structured packings. Okay.
Awesome. It looks like we have time for a couple more questions. This one says, does Koch have unique and proprietary designs for heat integrated distillation columns? It's a two-part question. And if so, what sets your approach and efficiency apart?
Yes. So in terms of heat integration, I mean, obviously there are the standard process engineering techniques of trying to recover heat that's present in, say, a distillate stream or a bottom stream to preheat something else in the process. So, you have heat integration by using heat exchangers and trying to get as much heat out of, internal process streams as you can. And then, as I showed in my last example, there is the possibility of using the vapors of one column under the right set of conditions, using the vapors from one column to reboil another column. We've done that a number of times. It's again, I call it multiple effect distillation because it's somewhat analogous to multiple effect evaporation. We've also used mechanical vapor recompression as a way of heat integrating or reducing the heat requirement of a process. And what that is, it's a technique that's been around for quite some time. It involves the compression of the overhead vapors of a column to a high enough pressure and temperature where when those vapors are condensed, there's a significant differential temperature between the bottom of the column and those condensing vapors. So basically using electrical energy to boost the pressure of a vapor from the top of a column to a high enough pressure and temperature where it can be used to reboil the bottom of a column. That doesn't work well in systems where there's a very large temperature difference between the components that you're trying to separate. If there's, a 20 to 30 degrees centigrade or less temperature difference between the top and the bottom of the column, you can typically use mechanical vapor recompression as a way of saving energy. I didn't hear. What? Can you repeat the last part of that question again?
I believe is what sets our approach apart.
Well, our approach is to evaluate as many different options as possible and present those to the client so they can see and then look at the return on investment of the various options. So the client has a choice. They can see, what the capital requirement is. There's always going to be additional capital required to try to reduce the energy footprint, so that they can make an evaluation as to what energy savings technique makes the most sense.
Awesome. All right, and one last question.
All right, we're almost out of time here.
Yep. When would you use distillation for solvent recovery from a liquid extraction process versus back extraction?
I'm not sure I can answer that one. Back extraction is normally used. We've used processes where we extract a solute into a solvent, and then we back extract the solute into a different solvent, and that's usually done, as I understand it, to get the solute away from some impurities that are in the feed and put them back into a different solvent. But solvent extraction is another topic in and of itself, and we have a technical seminar that's given by our subject matter expert, which is not me, on liquid extraction. So I'd like to know, whoever asked that question, I'd like to know if they were interested in listening to our technical seminar on liquid extraction.
Awesome. Well, those are some great questions. We are out of time. However, as mentioned, we'll provide an email that summarizes all questions and answers along with a link to recording of this presentation. Should any questions come up later or you have more project-specific questions, feel free to reach out to Tom or our team at the email addresses listed. Also, there's a short survey following the webinar. We would love some feedback and appreciate if you would take a minute or two to complete the survey so we can continue to improve our webinars and their content. Again, thank you for joining us today, and we look forward to seeing you at the next one.
Okay, thank you, everyone.